Right. So, in the previous lectures we have seen how simulators work. Now, we are going to see that how are we going to develop the simulation test plan. In other words, you see the simulator is only just as good as the test bench that we write. So, if the test bench does not cover all the interesting scenarios, then the verification is incomplete. Right. So, what is the way in which we plan the tests that have to be written for the given design. So, we are going to first look at the notion of hierarchical verification, because verification is typically done hierarchy at different levels of abstraction of the design. Then we are going to look at what is meant by a test plan and how is it developed. Then we are going to look at the emerging or the more popular notion of constrained random test generation, where the tests are not directly hand coded for each scenario, rather we develop models which randomly generate tests. And finally, we are going to talk about verification coverage, or in other words, that when we are running the simulation, what part of the design has been covered by the simulation, right. So, now to understand the basic problem here, we have this slide which says that exhaustive simulation is infeasible in practice. Why? So, let us consider a sequential circuit having some n flip flops and some m inputs. Okay. Now, what do we mean by verification by simulation? We want to reach each state from the initial state. So, we have to have a path to reach the initial state, and then once we have reached that state, we want to verify the behavior of the design from that state under all possible inputs, right. So, there are two aspects of this verification: reaching all the states, and then from those states testing whether the design behaves in the correct way, right. So, each directed test aims at reaching a particular state and giving some kind of inputs to see how it reacts to those inputs, right. That is called a directed test, because we know which state we want to reach, and then we know what inputs to give at that state, so that we are able to evaluate its behavior there. So, to look at a quick upper bound on the complexity of this is that if we have n flip flops, then the number of possible states is of the order of 2 to the power of n, and the number of input vectors at a given state is order of 2 to the power of m, because you have m input lines. So, you can have 2 to the power of m valuations of those inputs. So, to reach a state, we may have to pass through order s states in the worst case, we may have to go through all the other states in the worst case, and each transition will require an input vector, because from one state to another you will have to give input vectors to drive it from one to the other. So, the total number of input vectors that you are going to require is this order s times the order r, which is order of 2 to the power of m plus n, right. Now, this number is an enormous number. If you look at a reasonably large circuit like a processor, where you have several registers. So, suppose you have, even if you imagine you have 5 64-bit registers. So, that is 64 into 5 bits straight away for the number of states. Then you have the control state bits, and if you look at the inputs, and if you say that okay, my chip is going to have something like 20 inputs, then you have another 2 to the power of 20 to multiply with that 2 to the power of 64 into 10 or whatever, right. So, that figure is an impossible figure to be covered by simulation, right. So, what is the alternative? The alternative is that we must select a subset of input patterns. So, I have a question here. In the portion that you are studying on testing, have you started looking at test coverage, fault coverage? Right. So, we do not need to drive all those test vectors to cover all the faults. We actually look for a much smaller subset which can cover all those faults. Now, the good thing about testing is that the faults are known. You know what you have to cover. You know stacked fault in this line, stacked fault in this line, stacked fault in that line. Here what are you going to cover? We do not know where the bug is hiding, right. So, we do not know what has to be covered, and we cannot really go through all the states and all the transitions as we just now saw. So, we need what are called test scenarios. Now, these test scenarios, unlike testing, does not have a well defined formal coverage goal. There the fault model was the coverage goal. I know that this set of single stacked faults is my coverage goal. Here there is no such formal coverage goal, because we are trying to cover the functionality of the design. We are not trying to cover the structural faults in the design. Do you follow me? So, identifying the test plan and the test scenarios is an extremely non-trivial problem here, and we also have to define coverage. Now, these two are very closely related terms. Once you are able to define what are your test scenarios and what are the bugs that you are looking for, then you can talk about whether your simulation has covered those behaviors and those scenarios or not, right. So, coverage and definition of the test scenarios goes hand in hand. They are not two independent things, right. And the third thing is, what do we observe? Observability is a very important thing, both in testing as well as in verification. In testing, to have more observability, you have scan chains and things like that, where you have all the flip flops put in a single chain, and then when you want to see the state of the system, you just push out the value of the state by shifting the scan chain, right. Now, in verification, it is easier because you are simulating, so you can choose which points you want to monitor, right. But choosing that set of points is very important. Now, to give you an example, let us look at this simple processor. So, I have the instruction memory, I have a data memory, I have a register file here, and I have the ALU which is going to do most of the arithmetic operations. There is the program counter and the program counter logic which chooses the instructions from the instruction memory, right, and there is the internal bus which connects all these things together. Now, suppose we decide that we are going to observe only the IO or the interface of the processor, then what problem can happen? Suppose there is some error in the ALU. Now, for some combination of the operands, the ALU computes an incorrect value of the arithmetic. Suppose it is expected to do a subtraction, it for some value it does not do it correctly. For the rest of the types of operands, it might do it correctly, maybe some particular value. Now imagine the problem. That combination of value may have come into the data memory several instructions ago. Maybe one of those operands came in cycle 254, the next operand came into the memory maybe some 2000 cycles after that, and then those came into the inputs of the ALU another 400 cycles later, right. And then the output, the incorrect output of the ALU was stored back into the data memory or in some registers, and it remained there for maybe 50 more cycles before it got operated on by some other arithmetic, and finally it was put out of the CPU, and at that time you detected that the final value is not matching your golden output. You expected it to be 32, it is coming out to be 33. Now, debugging this thing is a major problem. Anvesh is smiling here because it is very closely related to the problem that he is doing right now. Now, what is happening here is that how are we going to go back and find out when and where the error occurred? If you have limited observability, this is a major problem, right, because it is easy to simulate it forward, it is not easy to simulate it backward and find out what happened there, and you cannot keep saving all the states, right, that is too expensive. So, we need more points of observation. So, one thing that one could do is that we put observation points, say we say that okay, let us observe this point, let us observe this point, let us observe this point. So, every time the ALU does something, we are able to check whether the ALU is doing it correctly. Then whether the data is flowing correctly is important thing. So, we put a observation point here and observation point here to make sure that the PC is working correctly. We put an observation point here, right, and then we see what is being written back by putting an observation point here, all right. So, we put a lot of observation points inside the circuit and monitor each of them during simulation. If you have a whole number of observation points, it is mind boggling. You will see a trace which has some 20 to 50 different waveforms. What are you going to debug out of it? No, it's mind boggling. So, we need to have automatic monitors which are sitting inside your code and checking those things that you would like to monitor manually. So, if you could have some way of saying what is the correct behavior of the ALU, for example, then you put in monitors that are going to automatically check in each cycle whether the output of the ALU is what it should be given the inputs of the ALU, all right. So, those are called checkers, and in recent times these checker languages have become quite powerful, and we call them assertions. Now, these assertions are plugged in everywhere. Wherever you want certain behaviors to be monitored all the time, rather than doing it manually by looking at the trace, you write an assertion which the simulation tool will continuously monitor over those observation points during the simulation, right.
So, how do these checkers evaluate? This one is if they have to match it with the output of ALU, how do they evaluate the actual output?
So, the checker is given the function that the ALU should actually implement. See, this is a circuit implementation, right. So, you know that you can implement an adder in 10 different ways. You can have a ripple carry adder, you can have a combinational adder, different types of adders you can have. Similarly, you can have different types of multipliers, but the multiplication function is the same, right. So, you can have a checker which just checks whether the product is actually the product of the two operands, right. So, in simple terms that is what the assertion does. The assertion says that when the instruction is mul, then given this operand the output should be this, right. We are going to see a whole lot of assertions, that is going to be one of our chapters. So, we are going to see how you can write assertions, code very complicated kinds of things in assertions, which can be monitored over several cycles, right. So, the assertion language is the one by which you code those assertions, and then the simulation tool parses that assertion and builds the monitor which checks that during simulation, right. So, that has become a very important part of the design debug process. Now, these are the main tasks that we have for bug hunting. Bug hunting is what we are doing, right. We have the design, we have the RTL of the design, we want to write tests to hunt for bugs, right. So, the main tasks are enumerating input possibilities with test plans. So, we will first write down that what are the things that we want to test. We want to enhance the output observability with assertions, and we want to bridge the gap between exhaustive search and practical execution with coverage measures. So, we know we cannot simulate everything. So, coverage measures are going to tell us what have we simulated, what have we covered, what is our degree of confidence in the simulation, right. Now, another thing that you must always remember is the taxonomy of the bugs is a very important thing. So, to give you an example, suppose I tell you that your bed has some bugs, right, and I ask you that can you search your bed and look for bugs, right. Now, the first thing that you will ask is that what do bugs look like. Now, if you do not know what bugs look like, then you will not be able to find bugs, you will not know which is a bug and which is not a bug. You can have different, if you pull up the mattress, you will have all kinds of things under it, right. Now, which ones of those are bugs, right. So, so you have to say, you have to find out which, so you need to have the taxonomy of bugs. So, similarly in verification there has to be a way in which you specify bugs, right, and then the bug hunting starts, right. And this today the way that this bug hunting takes place is in a hierarchical way. So, let us see what we mean by that. So, when we start the design of a reasonably large circuit, we start by looking at what is called a micro architectural specification. This is at the highest level of abstraction. This is where we specify the architecture of the design, right. I am going to show you some micro architectural specifications of some processors. So, from that you start developing the system specifications. So, the verification team sits down with the micro architectural specifications and starts figuring out that what are the tests that we have to do when I have the complete architecture designed, what tests do I have to run at that level. Then you have the unit level. What are the unit levels? They are the functional units. ALU is an unit, for example, right. The address decoder is an unit. So, you are going to look at the unit level blocks. Now, see, when we start developing the architecture, conceptually we go top down. So, we say that okay, this is a processor we want. Now, in that processor we are going to have this ALU, we are going to have this register file, we are going to have the mux, we are going to have the cache, right. So, those are the architectural units. Then those units in turn can be divided into further smaller units and so on, until the level of complexity of what you want to design is small enough for you to start coding. So, remember that in the design cycle we are going top down until we reach a level where we have the basic small blocks which we can start coding. So, coding starts at the bottom level here, right. Now, as long as you do not have the code, you can't verify, right. What you might say is that this partitioning of the design intent into its parts, the architectural decomposition, is that correct? Now, saying whether that is correct or not before having the implementation is a very difficult task, but it is also becoming a very important task. So, it is still in the research area, and we do a lot of research on that kind of thing, that how can you predict whether the way you are decomposing the design intent into the architectural blocks, the units and the smaller functional units, whether that planning is correct, whether functionally it is going to give me the correct design at the end. Because if that decomposition is incorrect, then what is going to happen is at the end when you have the full design, you will see it is not matching with the architecture, right. So, that is bad, but today there is no good way of doing that. So, what happens is that you go down to the lowest level and then start coding the small modules, the simplest modules. When you have built the simplest modules, let us say we have built this module, this module, okay. These modules are individually simulated. So, you write test benches for these modules, right, and simulate them. Like for example, some of you have written a shift and add multiplier, and you have written a test bench for that to simulate that, right. So, that is at the lowest level. Then you are going to have, once you have built all these modules, this unit becomes ready. So, you plug together these modules, or rather instantiate these modules in the larger module, which is the unit, and then you write an unit level test bench, which is going to test that unit. Then once you have the unit verified, you plug it into the full chip. When all the units are ready, you put it in the full chip and you write a test bench for the full chip, and the full chip simulation takes place. Just to give you an example of what is the magnitude of this, I once was able to see the way a Sun Spark processor was being simulated. So, a typical Sun Spark processor which has some 4 cores, 4 processors on the same chip, has an equal number of cache blocks, right. It typically has a distribution which has something like about 16 different directories, each directory containing something like a couple of megabytes of code, right, all in Verilog, and then this whole thing is simulated. So, that is simulating the processor, right, that is simulating the processor, and that processor, on top of that processor you boot Solaris. Now, remember the actual processor is not there, you are simulating the processor, and the processor is going to take instructions. What instructions? You boot Solaris on top of that, and then what do you do when you have Solaris? So, on your screen when you simulate, you will see that Solaris operating system is booting up, right. What do you do after you have booted Solaris? You start running Oracle on top of that, and on Oracle you start running some real data intensive applications, fetching from the database, storing it back. Whole thing is working on top of that virtual processor, which is getting simulated by the simulator, right. And this simulation, as you can imagine, is going to run into months, right. For months you will run this, and then look at errors, perform regression testing, and then again. Now, this, in spite of this kind of a mammoth exercise, the amount of coverage that you are able to get at the full chip level is hardly adequate, right, which is why we have to be very careful in finding out what kind of simulations we want to run, and that is why also a lot of this is moving to post silicon. Most of the major chip design companies are saying that this is too much for us to do. Why don't we create a first silicon, and then this full chip simulation we will do it in hardware, where we actually have the silicon. So, it is going to run at my 3.2 gigahertz speed, not in the 1 hertz speed which is going to happen if I simulate that thing, right. But the problem is observability. At the silicon you do not have observability. So, they are all well knit problems. We are going to discuss some of them from time to time. What do we verify at the system level? We verify the problem of interconnecting the subsystems that make up the system, right. So, have we connected the things correctly? Now, to do that, what we can do is that rather than taking the actual RTL of the units, you can replace the units by their functional models or behavioral models, and then check the interconnections at the top level using the behavioral model. This is becoming an increasingly popular practice. And the second problem at the full system level is to verify that the complete system is working correctly at the full chip level. This is a more tricky problem and the one that we discussed just now, and it has a very slow run time, and which is why hardware acceleration is preferred, and post silicon debug is the emerging strategy here, right. At the unit and module levels, you can do a lot more of testing to get a reasonable level of confidence. Now, the steps in creating a test plan are: extract the functionality from the architectural specifications, prioritize the functionality, everything is not important, we need to do the important things first, create test cases and track progress. Okay. Let us get down to some more concrete stuff. So, what we are going to do here is that look at these notations, that we denote by Q0 the set of valid initial states of the design. Q0 dash is the invalid initial states. Now, see, this does not mean that all states here are invalid, it means that as a initial state it is invalid, right. Some of these states, if they appear intermediately, they might be valid, but as initial states they are invalid, right. S is the set of valid states, S dash is the set of invalid states. So, we are not, the design is not supposed to reach these states, but note that these states are there, because if you have n state bits, then all 2 to the power of n states are there, you can't do anything about it. When we say invalid state, it is those states that we do not want to reach from the valid initial states. It is not that those states are not there, they are there, but we should not reach them, right. I is the set of valid inputs, I dash is the set of invalid inputs. Invalid inputs means that we do not expect these inputs to come. We are working this in an environment where those invalid inputs are not supposed to come, but they can come, and that is reality. So, our design will have to deal with invalid inputs when they come, right. These are the valid outputs, these are the invalid outputs. The design is not supposed to produce these outputs, right. The design should be producing these outputs. We will use this notation to denote that the design transits from state x to state y under the input I. So, this is one clock cycle transition, it transits from x to y under the input I. This one says that there is a sequence of transitions from x to y under the input sequence I. So, we are actually abusing the same notation here. This I actually refers to a sequence of inputs. So, when I start from x and apply this sequence of inputs, it is going to take me eventually to y. That is what this is denoting. We will use omega to denote do not care or wildcard entries. So, this is the entire set of behaviors of the design. We start from any, we are in any state, we give any input to reach any next state. Right. So, this is a transition system, present state, input, next state. Right. This whole thing is what we want to verify, but we can't because it is huge. Right. Now, we break down the set of test scenarios into 6 categories, and then we will prove that these 6 categories cover that entire gamut. So, if we have confidence in each of these 6 categories, then we have confidence in verifying the whole design. What are the 6 categories? These are the categories of test scenarios. So, we will build tests for each of these scenarios. First category is we start from any state and produce an invalid, we drive the circuit with an invalid input and see what is the next state, right. This is the first type of tests that we are going to do. Take your design and drive invalid inputs into it and see what the design does. This is something which often the designer ignores. The designer is always thinking of the valid inputs and whether it is working correctly on the valid inputs, but it also has to work under invalid inputs, right. There are requirements that has to be followed. You cannot say that the design is going to go haywire if I give you invalid inputs. So, this is case 1. Case 2 is, now this case 1 is relevant if the design is used in an unintended environment. Case 2 is that we start from an invalid state and then see if the design is able to, where the design goes. We see where the design goes under both valid and invalid inputs. So, this is to check whether if the design somehow reaches an invalid state, is it able to recover. This is another important thing that we have to test. Third thing is that we start from state S, which is a valid state, and we see that for, is it the case that for some valid input it goes to an invalid state. Now, if this happens, then this is a bug. This is a bug because it was in a valid state, we gave a valid input and it ended up in an invalid state. So, we need to design tests to see whether these kinds of transitions are possible. The fourth one is also an important thing. The third one was bug hunting. The fourth one is you want to see whether from a valid state on a valid input you go to a valid state or not. Now, covering these is an important thing. It is important to see whether the design is doing anything incorrect. It is also important to see that the design is doing all the correct things, that it is not incomplete. It may be correct, but it may be incomplete, right. So, that is why these 3 and 4, it is a little bit confusing that what is the difference between these things. This is checking for correctness, this is checking that it is adequate. Then the fifth category is that we start from any arbitrary state and see whether we can reach a valid initial state. These are called power on tests, that when you first switch on the circuit, is it able to reach from any state, whatever state it was initially, is it able to transit to a valid initial state, right. So, we need to develop tests for that. And then the last one is that, is it the case that I have some initial state of the circuit from where it is only going to invalid initial states, right. That is again the failure to power on properly, right. So, that again is a category of bug. Now, if we do tests for each of these 6 categories, we have covered everything, right. We will conclude this lecture with a proof of that. The proof is quite simple. So, let us look at that. Let us look at these two things first. If we test this one, which says that we start from any arbitrary state and reach a proper initial state, this is the power on, right. And if we look at this, where we start from any initial state and it reaches an invalid initial state. So, the tests for these two together is the set of tests for this, where we start from anything and we reach any initial state, valid or invalid, right. So, these two together covers this, right. Now, let us look at this. Starting from a valid state, on a valid input we reach invalid state. Starting from a valid state with a valid input, we reach a valid state. So, these two together tells us that we start from a valid state with a valid input and we reach some state, valid or invalid. We have covered both. If we have done this, if we have written tests for this, if we have written tests for this, then together we have written test for this whole case, that we start from any state, give valid inputs and reach some state. We have tested this. Now, if we combine this one that we have covered from here with the tests for starting with an invalid state and seeing where we reach, then we have together covered, these two will together has covered that we start from any state, because this starts from S, this starts from S dash. So, we have covered starting from any state and we give a valid input and see where it goes, right. Note that we do not have omega here, because S to omega is not yet covered, right. So, we have not yet covered the case where we start from S and then we go to omega, this part is not yet covered, right, because we have just tested starting from an initial valid state and giving a valid input, right. So, this is what we have essentially covered by virtue of this and this. Now, if we combine these test cases with the test cases that we have from omega to omega under invalid inputs, this was also one of the cases, right. This was one of the 6 cases, right. So, this one. So, if we take that with this with this, then we have actually covered everything, because we start from omega and then we have omega with valid inputs, omega with invalid inputs. So, we have covered everything. So, this proves that if each of the 6 categories are properly verified, then we have verified the all possible combinations, right. So, the test plan is going to target all those 6 categories one by one and develop test for that, all right. In the next lecture, we will take an example where we will start with these 6 categories and start taking examples of what kind of tests we need to do for each of those, right. and thereafter we are going to look at the ways of developing the test bench itself to code those tests.